Good day. Today, as you have seen, that we are going to discuss about the design for strength. Now, we understand that when a machine part fails, when stresses induced by external forces exceed their strength. So, this is very quite understandable. Now, the only thing is that we have to look that what is the meaning by the word strength. The strength means one we have can notice is that the property of the machine element. Now, what we understand by the property of the machine element means, suppose this is a machine element and which has been designed to take up some external loading onto it. So, once it has been designed, that whether it is put onto a machine member or it is simply lying onto the table or somewhere else, it is always going to have the strength for which it has been designed. So, that is the reason we call the property of that machine element. Strength is some sort of a property of that machine element. Similarly, property of the material is quite understandable, because the strength of an aluminum bar won't be the same as the strength of an say mild steel bar, or say for wood, for any other material for example. So, obviously, one of the important role is being played by the property of the material or the selection of the material for a design of a machine component. So, what we understand broadly by design, that means the design is something like that, the selection of optimum materials and dimensions to withstand failure due to applied load. See, I have underlined two cases, one is the failure and another is the applied load. So, obviously, some question comes that what we understand by the failure. Well, so obviously, if we think of a failure, then failure comes into two situations. One is the mechanical failure in materials, another is due to the type of applied load. So, that indicates the applied load. Let us have a look into these two aspects a little closer, that what we understand by the failure in materials. So, this failure in materials is normally designated as that mechanical failure in materials. So, you can see there are two criteria. One criteria, it is being written as yielding. So, what we understand by yielding? Yielding or permanent deformation is a sliding along certain angular planes in the materials. So, another one we understand is a fracture. Fracture is failure by separation that occurs on a cross section normal to the tension directions. That means, always if there is a failure of the material, then the failure of the material can take place, as we understand, either by yielding or by fracture. Now, whether it will be a yielding or it will be a fracture, it largely depends upon the type of material you choose for the design. So, in that way we classify the materials, as you know, you have read earlier also, that one is called the ductile material and we will take up shortly, another is the brittle material. Now, once we consider a material called ductile material, then what it is, its definition comes out to be? The ductile material definition is that its resistance to sliding is smaller than its resistance to separation. So, what we understand is that this particular situation we can just briefly explain over here. Suppose we take a specimen and we just put some applied load P along its axial direction. So, you understand the material is subjected to what we called a tension. Now, once we put the material in tension, then in this particular case what will happen, that if you have seen this type of material testing, then you must have noticed that this particular material, if it follows to the category of ductile material, then it undergoes some sort of reduction in area, cross sectional area at this particular zone. So, what we materialize? If we can see this particular figure, then I think it will be more clear that you must have seen that something like this, it comes down to something and this one, and well, some sort of situation comes, and ultimately this particular failure takes place in this zone. So, this is a line where the failure takes place. Now, as a matter of fact, although I have drawn a straight line over to show the failure is not exactly in a straight line. It forms in a some sort of what is very conventionally called as this as an cup, and another is some sort of a cone failure. That means this is a cup and cone failure that takes place in this particular case. So, when it is going like this, basically before this failure takes place, this particular shape comes out by sliding of the planes more or less at an angle of around 45 degree, and then gradually this elongates, and when it crosses the yield point, it goes to the blastic state, and then this fracture takes place. So, this is a peculiarity of a ductile material, and this ductile material failures on cup and cone shape, and as we have discussed earlier, this particular type of failure what we have just shown you is that failure purely by yielding. Now, in these cases what happens that the characteristics is as these materials can have same yield point value for both tension and compression. That means, what is happening, that what we have shown you just right now, tension, the particular material was in tension. Suppose it has undergone some compression also, then the experiments have shown that the ductile materials can have both the yielding, I mean for the yield points, both same value for tension and compression. So, this is that what we understand by a material ductile material, and the structural steels and most of the machine members well may not be a very precise, but still most of the machine members which undergoes shock, vibrations, etc., or anywhere in everyday life, we see the material of the designs are made by these ductile materials. Now, if we consider the next one, the brittle material, then what is the brittle material? The brittle material is its resistance to separation is smaller than its resistance to sliding. It is just opposite to that what we consider for the ductile material, and here the failure takes place by fracture. Now, what we understand, that means there is no sliding of this particular to the sliding what we have seen earlier for the case of ductile material, where the two layers of materials can have a relative sliding around 45 degree, but here it will have a sharp fracture separation, and this is considered to be an brittle material. Now, I mean we can see one situation is that if we consider again a bar, suppose we are having a bar, it is acted upon by a tension, by a torsion, suppose a T. That means you are twisting, giving a simple torsion to a material as I have shown you in this particular figure. So, if we apply a torsion in this manner, then what we understand, that if we consider a small elemental section from this material, then we know that this particular material is acted upon by an shear stress tau. Shear stress tau, we know that shear stress are complementary. That means we will have a shear stress like this and we have a shear stress like this. You remember that this shear stress we considered to be an positive because it is at with respect to a point inside the body, it is creating a clockwise rotation. So, this shear stress is an positive. Now, what happens that if we try to find out a situation of this particular state of stress through a Morse circle. So, what is that? We would like to just have a look at that one, that if we consider a Morse circle, I suppose you remember the Morse circle we discussed in the last class or maybe one or two classes earlier. So, we plot a sigma, we plot a tau, or the two axes for the Morse circle. And what is the state of stress? This we understand, this is an x plane, or what we consider the phi equals to 0. So, here we see only shear stress. So, if we plot a shear stress, now what is the other information? On the other information onto this point is a shear stress at this point. So, if we construct a circle, these points we join. So, this is the center of the circle, then we find that this comes out to be the Morse circle. Now, what is this one? This is phi equals to 0. What is this one? This is principal stress sigma 1 and this is principal stress, I mean the minimum one and the maximum one, and this comes out to be sigma 2. What is the magnitude of this one? We understand this is purely nothing but the tau, and plus tau and minus tau, that comes out to be this one. Now, what is the interest is that where at what plane this particular stress is occurring. You can see this angle is 90 degree, okay, this angle is 90 degree, we understand. So, obviously what is happening, that if we try to construct the orientation of the plane, how we do? It is 90 degrees. So, onto the element it moves out by an angle 45 degree. Okay. So, this is the plane. So, this is we consider as sigma 2, this is sigma 1, and this is the orientation of the plane where you get this particular feature. That means, this is the plane which is perpendicular to the plane is at sigma 1 acting. Now, if we look into a situation, see I have chosen a material chalk, a simple chalk has been chosen, and we apply a pure torsion onto the chalk. Just you can see that if I apply a pure torsion, then it is little hard. So, just see it has broken. Can you see the broken portion, how it has failed? So, it has just failed in the situation of this 45 degree line. I mean this both way, this is a 45 degree line. So, what is happening? If you consider this 45 degree line, can you not see it? It is resembling the same 45 degree line what we have drawn onto this particular plate over here. Okay. So, this is what is one small model I wanted to show you. Now, I will just have an explanation. Just see once again this particular plane. Okay. This is the plane you can see onto, this is the plane where you can see a failure, and correspondingly this is the plane where you can see the failure, and this is all at 45 degree as I have drawn onto this particular board. Now, you see What this test actually indicated? The test indicated nothing. Chalk is a brittle material. So, what is happening? Its resistance to separation is smaller than what its resistance, I mean its excuse me, its resistance to separation is smaller than its resistance to sliding. So, obviously, what happened, although it was acted upon by a pure torsion in some plane 45 degree, as I have shown you earlier, that the it was maximum principal stress. That means, it is just failing what? It is failing just perpendicular to the tension direction, that actually we have just earlier defined, that fracture is a failure by separation that occurs on a cross section normal to the tension direction. So, as because it happens to be a brittle material, the failure took place in that manner. Now, this is what we understand by brittle material, where failure takes place by fracture, and I have shown you what is a fracture. These materials mostly have higher ultimate strength values in compression than in tension. What is the ductile one? Ductile had more or less the same in tension and compression, but normally for the brittle material it has got a more strength in compression than in tension. Anyway, if you want to see a failure, I mean how the yielding takes place in cases of ductile material, one has to obviously go to and find out from the universal testing machine how the failure takes place. Well, which is a brittle material, what is a ductile material? Then you can see a rough guideline. If percentage elongation at fracture is less than 5%, then we consider this to be a brittle material, and ductile material, what we understand is that if the percentage elongation at fracture is more than 5%. Now, one of the situation that happens that that what has been mentioned over here, the ductile materials may fail by fracture if there is cyclic loading, long term static loading at elevated temperature, impact loading, work hardening, severe quenching. So, what are these concepts? Suppose, what is cyclic loading? Cyclic loading is an fatigue loading, what we will be learning little, I mean after some time. That means content continuously. If you consider a material member, suppose this way, and you just put a you just bend it like that, again you bend it on the other, like bend like this, bend again onto the reverse direction. So, what is happening? Suppose at the top fiber, if we consider, then continuously you are having in one cycle it is undergoing a tension, and at the next cycle what is undergoing? It is undergoing a compression. So, that is what we understand by a cyclic loading. What is a long term static loading at elevated temperature? That conventionally we call as a creep loading. Okay. Another one is called that impact loading. Impact loading you understand by these words, that is, if you are suddenly you are having an impact onto a machine member, then this is called impact loading, and due to that one also the ductile materials may fail by fracture. What is understand as ductile material may fail by fracture means something like that ductile materials may just behave like a brittle material. Now, for the impact loading, the one of the situations that can be coming into picture, as a matter of fact this happens, it happened rather that suppose a ship hull is built up by sheet metals by welding, and at normal temperature it is fine. Now, the ship goes to a very cold temperature, suppose at the cold zones in the ocean sides, and then if it goes over there, then what happens? Just due to that particular temperature effect, what happens? The brittle, that particular simple this mild steel which was behaving like an ductile material may just behave like an brittle material and fail, and these sort of incidents had occurred really in World War II, when the ships from say German side or like that, it goes to the Arctic oceans, I mean Arctic sites. So, the effect of temperature is also of severe situations combined with that impact, where a brittle material where a brittle material failure behavior can be exhibited in a ductile material too. Work hardening and severe quenchings are some sort of situations that occurs, these are metallography, the metallographic changes that takes place, and the behavior of the ductile material could be like an brittle material. Well, so that we have considered what is the type of failures normally due to this applied. Now we come down to another situation, the type of applied loads. So what we gather, if we just go through one step, that is a failure, mechanical failure in materials that we have just discussed, and then we just have a brief look at the type of applied load that can come into picture. See, obviously first one what we called as an static load, where the load does not change in magnitude and direction and normally increases gradually to a steady value. Even it is not mentioned here. I think if we can consider a situation that point of application of the loads are also not changing, means what I mean to say is that if there is a material and a load is acted upon by this way. So, this is the point of application, and with time this point of application of the load P is also not changing. But anyway, sometimes we understand a very small way changes in the either in the point of application or the magnitude of the loads coming into picture. We also call those situations a quasi-static, and there also the design could be considered just as the way we consider the design for the static load. So, here we understand what we understand by the word static loading. Now, we consider other situation, that is the variable load. What is the variable load? Variable load we understand is the changes in magnitude, it changes in direction too. So, we have given an example that traffic of varying weight passing a bridge. That means, you understand that onto the bridge continuously the changes is taking place. That means, one car is passing like that, again another car is passing like that. So, obviously, the bridge is not acted upon by a single magnitude, the point of application of the load is changing, the amount of magnitude of the load is changing, because the different vehicles have got their different weights. So, this is what we understand in the change in magnitude. Now, what is a change in direction? The change in direction is an example what you can see as a load on piston rod of a double acting cylinder. So, you understand that means if it is a double acting cylinder, then onto that particular one, once the, so what we can understand is something like this. It is some sort of, well, consider one. So, onto this one, suppose something is there to force, and then it is there on the transmission, and you have to design this rod. So, what is happening? This is just pressing this one, again the transmitting is keeping it back. So, there is a continuous movement in these directions. Okay. So, the load onto this rod is gradually changing. So, this particular changing pattern what we call as a change in direction. So, both together we consider the changes in magnitude, changes in direction, and that what it is causing the variable load. However, once we go for designing, then what we can see is that is a situation something like this. what we have considered is, say this is a time axis and this is your stress. Then what you can have, say a sinusoidal load pattern is going like this. Now, in this case what we understand is that this we denote as the maximum load, this we denote as the minimum load. So, what we get? We get somewhere a load line which we consider as sigma mean, or sometimes it is also denoted as sigma average or sigma mean. Sigma mean means we can denote is also something like this, something like that, sigma m also, that is also denote as a sigma m. So, this is a mean stress, and then what is it we call, consider this is an sigma a, what is a stress amplitude. Okay, that means this is a stress amplitude, that means whatever this is coming out to be, and this is a sigma mean line. From here it is a sigma mean line. So, some definitions are given for the sigma mean, that is an summation of this one by 2, this is an average, and the difference and divided by 2 is the this particular stress amplitude. We will be coming down to this derivations and the design aspects after a short while from now, or maybe in the 1 or 2 lectures after this will be decided. Now, these type of stresses we call as an fluctuating stress or fluctuating load. Now, once this is what we understand is a fluctuating load, as we have seen, that's time by stress if it is going in sinusoidal wave. In the similar manner, if we consider also another situation, say this is your time, this is your stress, and it is going like this. What we see, we find that this is sigma maximum, this as usual it is sigma minimum, and once we see this is an sigma minimum, that this comes out to be equals to 0, and again we can have a mean stress line, and as usual what you call is an stress amplitude sigma a, and this type of stresses we call as repeated stress. So, this is also a repeated stress or repeated load, and other one we can think of a situation that comes out to be something like this. This is a time axis, this is an stress axis, and we have some loading situation, something like this. This is sigma max, this we consider to be sigma mean. So, the magnitude of the sigma max and sigma mean is happens to be the same. So, that means this is coming out to be sigma mean, which comes out to be 0. So, average stress in this particular case coming out to be equals to 0. So, this is called as complete reverse stress. So, this is a complete reverse stress situation. So, what you having a situation like this. So, normally these are the three types of stresses that are taken care of while doing the designs. However, there could be other there are other various type of stresses that also we come across. Now, before coming down to this particular idea of what are the other type of stresses, let us be clear into one thing, is that the basic concept is that if you are having a mean stress line, then stress amplitude something over that one. So, if we consider the mean stress, then we consider the design to be a static, because mean stress is somewhat resembling a static load. So, this is a static load, and over which you are superimposing this the idea of a this type of what you call this fluctuating stresses or the repeated stresses or the complete reversal stresses. So, that means it is a mean stress over which sigma a, that means stress fluctuation or the that is being superimposed. That is the basic idea of the design. However, we will come down to this situation later on when we were considering the typical idea of the now. This is the variable load already we have discussed, and then we come down to the conditions that some other loading, which are the loads, this is useful loads due to the energy transmitted by the element, dead weight also taken up as a load, inertial forces, thermal stresses. Here thermal stresses is one thing that comes into picture. Due to the thermal expansion and contraction of the machine member, the temperature is causing a stress, and that stress sometimes if you consider in the analogy of load, that what we call as an thermal stress is also a type of loading. And also we consider the frictional forces to be the some sort of loading that we consider while designing a machine member. Now, this is one thing you can see the slides, that is a theories of failure. Now, what is this theories of failure? Let us have some idea what we understand by the design theories of failure. Look, if we see into this one, basically what is design? Load equals to stress into area, that we have learned, isn't it? As a very roughly we understand that load means a certain amount of stress into area. Now, this stress, if we remove the word stress by another word, I think you won't be having any objection. Strength into area. What is the difference? Let us have these two words, that once I use a stress, another I used an strength. See, if you are having a material, a machine member acted upon by a load P, you know at any section what is the stress? Any section 1, 2, 3, if you consider, the stress sigma will be equals to P by A. What is A? A is the cross sectional area equals to A. So, you understand the P sigma equals to P divided by A. So, what or other way, if we write out in this direction or this manner, then this comes out to be sigma multiplied by A. This is okay, it is acted upon by the load, this is okay, cross sectional area, that is the area. Now, we come down to this particular idea of the stress. Now, here we have written first earlier it is a stress, fine. When I write a strength, then what it implies? That if you go on increasing this load P, okay, then what will happen? At certain time the material will fail. Where it will fail? You can consider the failure to be yield failure. At the yield strength of the material it fails, means what is happening, and another case it is what I mean to by yield failure, because anyway once the machine member comes out to be an yielding zone, then it goes to a permanent deformation or it goes to a plastic state. So, that also we can consider to be a failure. Basically it is a failure because it will not come back to its original position. So, yield point is also an failure, and ultimate point is also another failure we consider. So, yield stress point, ultimate stress points, these are the certain characteristics, and those characteristics are nothing, as we discussed, the strength of the material. Means the material fails, that whenever it crosses the strength of the material, that is the property of the material is a strength, and that is defined by yield point or the ultimate point. So, those that is the reason what I am trying to say, indicate that here you can see the stress generated will have a maximum limit, and that will be, that is our consideration, where we will be considering, say we consider to be yield strength. So, yield strength of the material multiplied by area is a maximum amount of load. In other words, the stress what is generated can go maximum up to the yield strength value of this material. Why? Because you can see this material was in pure tension. So, the stress generated and the strength of the material could be put 1:1. What I mean to say? The maximum stress that can come into the material and the strength of the material can be well related, because we are only having a stress in one direction, and that stress can have a maximum value which is equal to the strength of that material. So, you understand, that means stress is at a point, and that stress at a point, sometimes that stress at a point when it reaches a maximum, we can say that is a strength of the material. And this analogy, or putting the stress directly equating to the strength as a yield point of the material or the ultimate stress of the material, is very easy, means it is understandable. Suppose in addition to that, we have a member acted upon by various loads like that, various loads of the torque, then loading applied like this, some loads actually like this. Then if we take up a stress element somewhere over here, a small element, we have seen earlier that this particular element can have a, say, sigma A, sigma B. If we consider a 3-dimensional aspect, then it can have also a sigma C, something like that. That means it is acted upon by stresses at various directions. So, if it is so, then we understand that stresses, we are having multitude of stresses, but what is the strength? That means stress many, okay, but what is understand by strength? Strength is only one, say yield point. So, there are many stresses at different points, and but there is only one strength of that material. So, unlike the simplest situation, here what we have to find out? We have to find out the stress at a typical point or the different points at the what we primarily talk about as an critical points, and then only we can equate it with a strength of the material, which primarily is a one side. The material can either you can consider the yield strength of the material or the ultimate strength of the material. So, the strength of the material is basically coming out to be 1. So, that is the reason we are having the concept of theories of failure. That means, the people or the engineers, they have derived many conditions, that is what are the suitable conditions for which you define the material will fail. So, while considering the theories of failures, we consider in two aspects. One aspect is the failure theories that are I will discuss about the failure theories, which will be primarily used for the design of maximum shear design of ductile materials, machine components built of ductile materials, and we consider some theories which are quite appropriate for consideration of the brittle materials. Now, one of such theories for the design of ductile material comes out to be maximum shear stress theory. It is also known as Tresca theory. It states that yielding would occur when the maximum shear stress exceeds the shear stress at the tensile yield point. As it is written below, this criteria agrees well with the experiment. Now, what we understand that yielding would occur when the maximum shear stress exceeds the shear stress at the tensile yield point. Now, let us have a brief discussion on this particular aspect. Suppose a material, as I told you earlier, can have, say, the stresses sigma A, something like that, it is sigma B, what is an, it is an sigma C, I am sorry, this is sigma C, and let us write it clearly, this is sigma A. Now, consider a situation something like this, sigma A greater than sigma B greater than sigma C, and to consider in two dimensional aspects, say let us put the sigma C to be 0. Now, in that aspect, if we draw a Mohs circle for this situation, then we can see a situation, it is Mohs circles between sigma, suppose we consider viewing from the top sigma C and sigma A. So, we get a Mohs circle like that. Suppose we consider a situation between sigma A and sigma B. Suppose sigma A, sigma B of the same sign, that means it is like this, and between B and C we can find out these are the stresses. What is this one? These are the Mohs circles. I think I need not again describe the Mohs circle. So, these are the Mohs circles for this situation. So, this is sigma A, let us consider this is sigma A, and sigma C comes out to be 0. Now, as per the criteria, what it says, that is at this position for the outer Mohs circle, what is the value of this tau max? This tau max is nothing but the radius of the Mohs circle. So, tau max equals to sigma A minus sigma C by 2, and this now I write as 0, that means it is just coming out to be sigma A by 2. Now, if we consider a material made of the same material for which the machine component has been built, it is acted upon by stresses, by loads, and in this case when the load comes out to be yield point load, then we get a this corresponding to the load which is creating an yield point. Okay, you understand, this is the yield point corresponding a load P. So, the stress element will be something like sigma yield point. Okay. Then what is representation onto this particular okay, I require this much position only. So, that will be in a Morse circle. This is what? Sigma yield point, this is 0. So, this is what we are getting. Am I correct? So, this comes out to be tau max. So, that's equals to what? If the criteria what you wanted to know, the yielding would occur when the maximum shear stress exceeds the shear stress at the tensile yield point. So, you remember, so what we get? So, what we get? That sigma A by 2 should be less than sigma yield point by 2, or sigma A is something less than sigma yield point. Now, we consider to be more generalized by a situation, I think that will be much more better, and that is what we consider to be as something like this, that sigma A sigma yield point, the 2 cancels out, sigma B less than sigma yield point. That could be also another possibility if sigma B is more. And what I did not show you, suppose sigma A is of positive magnitude and sigma B is of the negative, it's a reverse, then what is happening you can understand, then tau max sigma A minus sigma B. So, in that case the modulus of sigma A minus sigma B should be sigma yield point. So, you understand that what is the meaning is that if we consider these equations, then this is when sigma A and sigma B are of the same sign, and this denotes what? That sigma A and sigma B are of opposite sign. So, these are the situations what is being expressed. So, the ultimately what we get the maximum shear stress theory as outlined over here. That means how you design it, that means once you find out the that particular one, what you find out this particular stress at this level, and this stress should be what? Less than this one. You remember this particular sigma yield point, how it has come? Basically it is tau max, and that has come out to be sigma yield point by 2. So, 2 cancel. So, we are writing a sigma yield point. So, that means this is now I am just erasing out. So, what is this? This is a material property, material strength. That means, when a stress at a point is now can be related to this particular situation. So, it is a biaxial state of stress. So, depending upon the designer, he will be finding out the critical sections, and thereby he can represents the theory in this manner. Now, if we put these results, then you can see the 3 conditions. If I write down this sigma A, sigma yield point, sigma B less than sigma yield point, you understand, same sign, and sigma A minus sigma B modulus less than sigma yield point. Then what is happening? If you plot this, all these situations, then this axis is sigma A, this axis is sigma B, then you get something like this. Anyway, this is your sigma yield point. This point is bounded by all as a sigma yield points like this. Okay. So, any stress values bounded with this zone is a safe stress. So, this is what we called is a maximum shear stress theory. What is this is called? This is sometimes is called Tresca hexagon. Now, this is a very useful tool in the designing, and if you can see that by the simple tension test, what we can find, that sigma yield point we can find from the simple tension test. So, by this theory, what it is being predicted, that tau yield point should be how much? If we consider this one, tau yield point should be sigma yield point by 2, or that is equals to 0.5 sigma yield point. It is not exactly, but it is quite close to the experiment. Well, we have other theories which I think we can continue in the next class. Thank you. Good day. We continue our lecture on the design for strength from the earlier class. So, we had just a very quick recapitulation of what we discussed last class. We had discussed about that maximum shear stress theory, which also is called as an Tresca theory. And what we have seen, that yielding would occur when maximum shear stress exceeds the shear stress at the tensile yield point. And in the on this regard, we found out what we did. We have seen that we got some relations, that if this is sigma A, sigma B, the envelope was something like this. I am having these values of yield point, sigma yield point. Anyway, you can give also a minus sign over here, and these are also bounded by these things. And we got the equations of the form sigma A for a safe design, sigma b modulus for the safe design, and sigma a minus sigma b for the safe design again comes out to be yield point. Well, sometimes we can also use an equality to get the extreme value in the simple tension test, and in simple compression tests is the same, but it is not, because what happens when you use the brittle materials, then the flaws or some other material defects will be more pronounced if it is acted upon by a tensile test. But if it is acted upon by a compressive stress, or the compressive stress on the other hand, then what we will be finding out that the material can take up a more and more load. So, in general, as it has been earlier, last lecture when we have discussed about that materials, we have told something that the brittle materials normally have the more values in the compressive stress compared to what we get in the tensile test. So, just to overcome this situation, the drawbacks of this maximum principal stress theory, then what has been suggested is that another idea that is called Mohs failure criteria. Now, one thing I would like to say, that is, in the Mohs failure also, the material what the people considers is a brittle material. So, now what we have learned? We have learned two situations. That means two situations means one for the brittle material, another for the ductile material. We discussed about the ductile material. The two popular theories are what? The maximum shear stress theory and the distortion energy theory, and for the brittle material we consider the situation which is called the Mohs failure criteria and maximum normal stress theory. So, these are very important situations. That means these four theories: maximum shear stress theory, Tresca theory, distortion energy theory. This is for the, both are for the ductile material. Then next comes to the maximum principal stress theory, and then we find out the Mohs failure criteria. Now, with